So I am delighted to say we've got our first external speaker now. So we've got Professor Mike Zdilla on the call. Mike is a professor of chemistry at Temple University, and his group is interested in looking at the interface between inorganic chemistry and other disciplines, including biology, energy, and nanotechnology. Importantly for today, Mike is passionate about education. So he created the database of crystallographic online resources known as Decor, which I'm delighted to say we're now able to host at CCDC thanks to Mike's efforts. And he also uses the Cambridge Structural Database in his teaching. So Mike will be sharing with us this afternoon how he uses the CSD and Mercury in teaching. And so I'm going to pass over to Mike for his talk.
Well, thank you so much, Suze, for the introduction. Can you guys see my screen?
We can, and we can hear you.
All right, good. Hopefully this goes well. The GoToMeeting menus are all over my actual presentation screen, and I'm not sure how to move them, but I'm gonna do what I can and present to you today a little bit about the crystallographic education mission I've kind of been on since coming to Temple, and how that has been supported by CCDC, which plays a significant part in that. But first, just a little bit about me. So I was a graduate student for Sunny Lee, who's a synthetic inorganic chemist. And Sunny really wanted his students to understand the crystallographic experiment as much as possible because it's such a central part of our work. Let me make sure I get my laser pointer thing here. There we go. But I learned crystallography not from Sunny, but from Doug Ho. I don't know if you can see my laser. I'm actually having to put my mouse over the GoToMeeting menus, so you may not be able to see it, but he's indicated by the arrow. So Doug was my crystallographic mentor who taught me how to do structures, and he was a very diligent and detail-oriented teacher. But you know, the nature of learning crystallography when you work in a lab is that, you know, it's a practical education. You learn how to treat the data. You learn when to do, you know, when to do what, and how to go about it. You know, how to go about solving certain pitfalls. But there's really, you know, there's not much of an opportunity for a base level theoretical understanding. And of course, Doug has that understanding and would answer my questions appropriately when I was confused about certain things. But I never sort of felt I really fully understand what was underneath all of the software and all of the steps. After being at Princeton, I postdoced at Purdue for Mahdi Abu Omar, and I didn't really do any crystallography there, but I did become friends with Phil Fanwick, who was the crystallographer at Purdue at the time, and had lots of great conversations about crystallography, including crystallographic education, because Phil did teach a crystallography course for grad students, where he did cover some of the theory, and I actually started learning a few things about structure factors and so forth by sitting in on that class. But when I was heading off to become an assistant professor, it became very clear that they actually wanted me to teach a course in crystallography, which I found a little intimidating because I really had never taken one, even though I knew how to do the experiment. And so I started having conversations with Phil, and he shared with me this article that he wrote, Observations on Crystallographic Education, which was fairly new at that time. And it really has sort of formed a bit of my mantra and how I think about the importance of crystallographic education. And as Jürgen pointed out, it's so important to so many disciplines. It's such a central technique, but that it really gets very little representation in the curricula, unless you happen to be one of the lucky few that pursues it as a big part of your research or as your career. You really don't get a detailed understanding of it. So we kind of bifurcate into people who become experts or people who know next to nothing about it. And so at most you might, do a powder diffraction experiment in P-Chem, or do a training workshop to learn how to use the instrument, or if if it becomes a central part of your work, you learn through a practical training as I did, and I suspect many of you had. But upon coming to Temple, I really wanted to develop a traditional undergraduate type course, an advanced laboratory course, completely devoted to this topic. And I know there are a number of these around the country. They're not terribly common, but others do exist. But there are few enough of them that, I basically had to build this up from scratch. And so basically what I have here, and I'm going to refer back to this a bunch, it's sort of a visual syllabus of my course. And it's structured based on Werner Masse's book, Crystal Structure Determination, and the top sort of shows how that book is organized and how the lecture topics are organized. But then interspersed with that, we have a lab where we use the Bruker suite along with ShellX, OLX2, and Platon and CCDC software, where we go along, and rather than just sitting you down and mounting a crystal and going through and showing you how to solve and refine it, we do this step by step. Right? We just do an indexing lab, and then we do a space group determination lab, and we do this alongside the lectures so that students can sort of understand what's behind each step of the crystallographic experiment. So here's the two books. Werner Masse's book, which I think is a great scrutable book for undergraduates. It doesn't really go into much math, not much more than is necessary, arguably perhaps less than is necessary, but it doesn't overwhelm the students, but it gives a good, correct and succinct description of the theory. And then this really is my book, which didn't start as a book. It started as a bunch of handouts that accompany the labs, but which has now been assembled into a book. Which I haven't posted anywhere, but I'm happy to share the book and the data with anybody who would be interested in using it. But what I want to do is just kind of go through a few examples of how the lecture and the lab are integrated, and then give a couple examples where CCDC comes into it. What we start with in the Werner Masse book is unit cells and Bravais lattices, which I kind of present as two topics here. And along with the lectures and the reading, I've developed these homework problems. So for instance, questions to see if they understand the concept of the Cartesian coordinates in a cell. So here's some questions where they have to calculate interatomic distances in angstroms, but I've just given them the coordinates and the unit cell. There's some conceptual questions, why is there no triclinic C cell, and they have to draw a picture that shows why. And so while they're learning about lattices and unit cells and Bravais lattices, we go into the lab, and we start out with something that doesn't really require any crystallographic theoretical knowledge, and that's growing crystals. So in this class, there's only 2 points where the students step into a chemical lab. And the first is right away, they go in and they just grow some crystals. That's actually of a modified biphenyl compound that we use in this class, a methoxybromobiphenyl. And then at some point, it's not necessarily the second thing they do, but at some point in the semester, once those crystals are grown, we step into the X-ray lab, and I show them how to mount the crystal and collect the data. And so this kind of goes in parallel with the first few lecture topics, which really you don't need lecture knowledge, theoretical knowledge to do those first 2 steps. So that's how the lab part starts. And meanwhile, the lecture continues for a number of weeks, 4 to 5 weeks, before we get up to the point that we've introduced the Bragg equation, reciprocal space, and the Ewald sphere, which I feel knowledge of all of those is important before you even look at an X-ray photograph. And the reason I think so is, of course, we teach the Bragg equation even in P-Chem, but in this class we go into the Bravais lattices and what we mean and how you plot them, and how they relate to reciprocal space. So this is an example of an assignment, a worksheet assignment the students get to do, where they have to draw the Bragg planes, draw the D vectors that come out of the Bragg equation, and then in reciprocal space, plot the D star, the scattering vector, and and hopefully illustrate to them that D and D star are parallel. So the 111D and the 111D star are parallel, but they're reciprocals in their length. So, you know, the shorter D vectors the longer D vectors represent shorter D star vectors, although they're parallel to each other. And the shorter D vectors represent longer D star vectors in reciprocal space, and they sort of plot these things and begin to understand how reciprocal space is organized. But then for me, the most fun lecture is to present the Ewald construction, and you know, this is kind of the big reveal that the reciprocal lattice, which seemed like an abstract way to organize your thoughts, is actually the diffraction pattern, and show them that, you know, the diffraction image is actually a 2D slice through the reciprocal lattice. And at that point, I think it becomes appropriate to go into the lab and start looking at X-ray photographs, because only then do you really understand, does the student really understand what they're looking at. So I just want to show a couple snippets from the lab manual here, and how, you know, we try to not rush through these experiments, and we try to stop and think about what's going on when you index a cell. So here's what the lab looks like. It's a little dry, right? It's step-by-step instructions in terms of what to do with the software, you know, how to load up your sample and so forth. And, you know, how to describe the crystal. In most labs, we show them what the compound is. Reality and crystallography, we usually know what we're putting on the machine. We do have one experiment where I don't tell them what they've got and they have to figure it out, which is kind of fun. But in most cases, you know, they know what they're going to be looking at and they're following the instructions. But then as they go through, we stop and we think about what we're looking at. So, you know, in this instance, I instruct them to turn on the resolution ring in the Bruker indexing software and pick the highest angle spot, which happens to be this one in this photograph, and determine its resolution with the resolution ring. And then I'll ask them these questions. So they can't just rush through this. They have to stop and read the questions and think about them, and then write down the answers that they get out of the software. And then another thing that I think was pretty clever that we came up with, that I actually came up with the help of a colleague, is that at the back of each one of these labs in the book, there's a perforated answer sheet that they can rip out, and then they fill in their answers to each question here, and then this is something they can turn in for a grade. That makes the grading pretty simple in this class, makes sure that they get some credit for participating and for putting some thought into these questions. And then here's another fun question that we get to think about. What they've learned about Bravais lattices is after you've indexed the cell, you know, you see the unit cell parameters here, A, B, C, alpha, beta, gamma. But before you've chosen the Bravais lattice, I stop them and I say, okay, what do you think this Bravais lattice is? And they have to go back and they have to think about the restrictions, and hopefully they notice, oh, this looks like all 90 degrees, so it's probably not triclinic or monoclinic. And then this becomes a fun sample because they look at these 15.21 and 15.61. Well, are those really different, or are they the same? And we see if the students can guess whether, you know, how many of them are going to guess tetragonal and say, oh, these are probably the same, and how many of them are going to guess orthorhombic, and we have some fun and see who's going to be right and wrong. Of course, all the students get full credit whether they've guessed tetragonal or orthorhombic. I don't expect them to know that 0.4 angstroms is a very significant difference, but then they go on and they can see that, you know, while tetragonal gets a higher score, you know, 0.2 higher than cubic, it's quite clear to the software that this is not a tetragonal crystal. So as they're going through and doing this routine stuff that we do at high speed in the labs, they're actually thinking about the theory. We then go back, after they've indexed, we go back to these X-ray photographs, and in the Bruker software, it's nice because you can position your mouse somewhere in the photograph and the software will report for you the HKL values once the cell's indexed, so you can go in and ask the student, you know, find the highest angle spot and what's its HKL index. And they can see that it's, you know, that it's 5 minus 14 minus 1, and connect that, you know, these dots are not just, you know, random stars in a sky, but they're part of a grid intersecting the Ewald sphere, and each one of these has a Cartesian coordinate, and they can write it down. And then another fun plugin is the R-Lat Viewer, so that they can rotate around. We can ask them which reciprocal cell vector is longest, and they should notice that that's opposite of which direct cell is longest. So A is the shortest, so A star is the longest. And it's also fun. I love pointing this out that, you know, in these R-Lat images, if you rotate them the right way, you can see the shape of the Ewald sphere where it has cut through the reciprocal lattice. And they find that really interesting, and seeing this abstract concept kind of visualized in this R-Lat image. After we do that, they get a homework assignment. So here's where CCDC comes into it a little bit for the first time. As a crystallographer, after you index your cell, it's wise to go check and see if it's a known thing before you spend time and resources collecting and solving it. So they get a homework assignment where we send them to the CCDC to do a unit cell search and see if they can find out if that structure exists. And so they know what it is, and so there's these step-by-step instructions in the homework to plug in your unit cell, and so they can do this and do the unit cell search, and lo and behold, they'll search through, in the third or fourth result, they'll see that this compound exists. And then this becomes an opportunity to teach them about searching the literature for SIFs of known structures. So then we have them download the SIF. They can rotate it around, and now not only do they know what to do as a practical crystallographer, they know how to search the literature, use the CSD to search for structures. I teach them a little bit about the use of mercury, which is a nice viewer, but what I really love about mercury, it has some really cool utilities for viewing crystal packing and appreciating intermolecular contacts, which I have them do in this assignment. And then one of my favorite things that mercury does is predict the powder pattern. So I show them how, if they want to know what the powder pattern looks like of some compound that they can't get a single crystal of, they can't index it, but they want to know if they got the right thing, you just pull down the SIF from the CCDC and it will calculate the powder pattern for them. So that's a fun thing that we do with them. I don't have a lot of time left. I wish I could take you through the whole course, but I definitely can't. But there's a couple other things that I just want to show you. In the symmetry chapter, we, of course, explain the new, when I say new, I mean the symmetry elements you don't learn in inorganic chemistry, the screw axes, roto-inversions, and glide planes. And I tap into these animations from Wojtek Jankic, which are really illustrative, but we really spend a lot of time on the space group tables, and they suffer through this, and I get them to the point of answering hard questions where I'll circle this atom and I'll say, if we operate on this with the A glide, you know, which atom does it become? And they really grapple with these 3D symmetry operations in the space group tables. But then we go and we apply. I'm just going to skip ahead here. We apply that when we get to the symmetry determination experiment in the computer lab. We stop and we think carefully about the things we've learned in lecture. You know, when I'm going through XPrep, like many of you, you're probably just going enter, 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 and just zipping through things, especially if you know you have good data. But we stop and we look at these things, you know, have the students look at the intensity statistics, the E squared minus 1, and see if they can predict whether they're going to get a centric or non-centric cell. Have them look at the systematic absence exceptions table and try to predict which symmetry elements they're going to have. So, you know, hopefully they would see there's only 2 violations for a C glide, only 1 violation for a 2-1 screw axis, and figure out, before XPrep tells you, figure out what symmetry elements are there. And then go in and look at the reciprocal space, the intensity weighted reciprocal lattice plots, and connect that into what they've learned in lecture about systematic absences and how they relate to symmetry elements. So they'll go and look at this, and they'll see that you know, in this space group, which was go back, which one it was, PBCA, I think. Oh yeah, it's shown at the bottom there, PBCA, that they can see that there is a systematic absence there that they expect from the 3 glide planes that are present in this space group, and then you know, make that connection to the homework problems that they've done looking at the space group tables. Other fun things we do in the course, we have them solve a Patterson structure by hand, and I'm being a little facetious with that. Of course, they don't phase every single spot, but you know, I have them look in the space group tables at the symmetry elements in a sample space group, in this example P21212, and they can write the expressions for the Harker peaks, and then we can show them, what the Fourier transform real data would look like, and they go in and they can assign those Harker peaks they've worked out to these actual experimental Harker peak positions and figure out their X, Y's, and Z's. And then I don't have them solve the whole structure, but I'll give them a single spot, and I'll say, use those 4 iodine atoms to approximate the phase of, the 3-1. I think this is the 1-3-1 spot. Yeah, the 1-3-1 spot, and they've got to do the vector sum and phase a spot. And it's sort of like, solving a Patterson structure by hand. We have them look at some practice problems on direct methods. So this is a fake data set of like, 9 or 10 spots, and they have to identify quartet relationships and triplet relationships where the indices sum to each other, and they've learned the rules about phasing, and then they'll figure out that the doublets have to be positive, and then they can go and they can figure out what other peak can be positive, and they have to make guesses as to what's going to be positive and negative and see if they can get them to match up. So of course a human cannot do a direct method solution, but it's a little mini phasing exercise to sort of understand what the computer is doing. And then of course we have them edit the CIF at the end of the experiment, and I love Encipher, another CCDC program, so they learn to edit their CIF and check it with Encipher. So the last thing I just want to point out, my time is up, but I've developed all of these teaching tools, and I had always wished that there was a repository where I could draw from. And so I've really been working with CCDC a lot lately, because I started out by posting the teaching materials I had made on this resource called Decor that I developed, the database of educational crystallographic online resources. And I kind of wrote it myself in HTML, and then I started soliciting education materials from other colleagues, crystallographic colleagues, and building it up. But it was really a slog because I didn't have the time and resources to do it myself. And so now I'm really grateful to the CCDC that they've picked it up. So this is, then versus now, what it looks like then and now. And since they've taken over it, it's now getting more entries and more contributors, and it's growing, which is what I always wanted it to do. And so that's I believe Yinka Olatunji-Ojo is going to speak a little bit more about Decor later. I would have talked more about it, but I think it's going to be presented. But basically, I'm out of time, so I'm just going to jump to the closing slide. And NSF supported a lot of the work on programming and setting up Decor, as well as the CCDC, who is now hosting it. So thank you very much for listening, and I'd be happy to take your questions. I can see that some of them are here in the chat. Do I have time to answer some questions?
Yeah, you do. Thank you for a great talk. Really interesting to see, I think, how visual some of your lectures are as well, and how you kind of engage students. You have got a few questions in the chat box. We'll take a few minutes to do the questions before we go to coffee. So I think the first question was from Bill about time allocated to the course, how many hours of lectures and how many hours of practical, and what's kind of the split between.
So there is. Yeah, so this Bill Clegg asked, you must have a lot of time allocated to this course, much more than most universities will provide. How many hours of lectures and how many hours of practical? So it's a lab course, which means that at Temple, those are mostly 4 credits or 5 credits. It actually started out as 5 credits, and I actually chopped it down to 4 because I felt I wasn't using all the time I had originally planned for. And the reason is it takes 4 to 5 weeks before we're really ready to go into the computer lab and index. But once we hit the 4-week mark, it's 2 lectures per week. It's a Tuesday, Thursday lecture for an hour and a half. And then it's about 1 lab per week, mostly in the second half of the course. So in the first half of the course, we don't get into the lab as much, but then we make up the distance in the second half of the course, and the labs are mostly 3-hour computer labs as they go through these experiments. So if you add all that together, and then some weeks in the second half, we go to lab twice a week, so both Tuesday and Thursday. So in the end, it adds up to be like a Gen Chem, right? So a 3-credit lecture, one credit lab, which means 3 hours per week in the lab, which mostly is the computer lab. So it works out pretty cleanly, even though it's kind of broken up into odd chunks.
Nice. And how many students do you have in the class? A question.
Right. So it's been a pretty popular course. So Temple's a large school. We have almost 40,000 students. So this is an upper level, senior level class. So I think we wouldn't be able to run this if we were a small institution because it would probably be too under attended. But it's about 12 to 17 students usually. Which is a good number. We can't really do much more than that in our computer lab. We would have to expand our computer lab if we went above that. Although with COVID, for the first time, it got canceled because I only got 1 student registered because so many of our seniors decided to take a semester off. But normally, I'd say a typical semester is about 15 students. And I think I've answered the credit hour question there.
You have. So I'm conscious of time, so I'm going to thank you again, Mike, for a fantastic talk. Really enjoyable. I would stress that we're not going to test people on their space groups after.
Yeah, right. Well, that's why you need a whole semester course. You can't just show it in a lecture and expect people to know it.
So we're going to go into a coffee break now. When we return, we're going to be returning on the hour. So UK time, that is 4 o'clock. And we're going to then be hearing from Dr. Jessica Wade. If you do have any questions over coffee, I'm sure Mike will be happy to answer those over the coffee break as well.
Yeah, I'll sit around here. If anybody just wants to unmute and ask, I'll certainly talk some more.
And we'll see everyone else at 4 o'clock.